This is Unit 2, the atmosphere, for day 4 of class, our heat transfer and climate. So this will be, for your notes, your learning target 2.d, which is heat transfer and climate. We'll be able to read and interpret climate graphs, label global climate zones, and illustrate the basic movement of surface ocean currents on a map, define conduction, convection, and radiation, and relate these terms to the Earth's atmosphere, describe energy transfer and global wind patterns, and describe the direction of global winds, specifically our trade winds, westerlies, polar easterlies, doldrums, and jet streams. Insolation. All this is incoming solar radiation. It's coming in, sol for sun, okay? So insolation, our incoming sun. This is what's going to drive our winds. It evaporates water and causes weather changes on Earth. When we're talking about different types of energy transfer, we have radiation, which is energy that travels in the form of waves, conduction, which is energy that transfers between atoms that are touching, and convection. This is energy that transfers due to the movement of liquids due to the differences in temperature. This is where our hot stuff goes up, cold stuff goes down. So this is one of the diagrams that you have to fill out in your notes. Okay, so the sun heats the ground through radiation. The ground, in turn, heats the air right above it through conduction, because the atoms of air are touching the atoms on the surface of the ground. Then, once it leaves the surface, our warm air is going to rise. Okay, that's convection. So when we look at air pressure, this is the force exerted on you by the weight of tiny particles of air. When air is compressed, air is said to be under high pressure. That's just like if we look at this diagram over here. This person down here has a lot of weight pressing down on them, so they would be under high pressure. The person that's up here all the way up in the air is going to have low pressure because no one's standing on them. All right, so our insolation, air pressure, and wind. Unequal heating of Earth's surface causes our air to rise faster in some areas and slower in others. This results in differences in air pressure. Our rising air is going to cause low pressure at the surface, and our sinking air is going to cause high pressure. So when we look over here, if this area gets very warm, because hot things go up, all of the air is going to rise here. If I have it going up, I have low pressure at the surface. Over here, I have air coming down. So it's getting all packed in at the surface. So I'm going to have high pressure down here. Now our wind is always going to blow from areas of high pressure to areas of low pressure. Just like a ball rolling downhill, it's going to roll from a high area to a low area. If we look at our map of our differences in insolation, remember insolation is our incoming sun. Okay, so in January, you notice how the southern hemisphere is much warmer than our northern hemisphere. And in July, you see that our northern hemisphere is much warmer than our southern hemisphere. This is because our seasons, okay? So our differences in insolation is due to Earth's seasons. In winter, in the northern hemisphere, we have shorter days and longer nights. Okay? During our summer solstice, we have longer days and shorter nights. Coriolis effect. This is a very difficult concept to understand. So this is basically the apparent bending of anything moving on Earth due to its rotation. Okay? Earth rotates from west to east. If we're looking down on the North Pole, so if I'm looking down from up here, it looks like it's spinning counterclockwise. If I'm looking up from the South Pole, it looks like it's rotating clockwise. So our apparent bending in the northern hemisphere is to the right. So if I have an object or wind moving straight north, it looks like it's bending to the right. Even this area over here, if it's supposed to be going that way, it looks like it's bending to the right. Same thing here, it's bending to the right. So everything north of the equator looks like it bends to the right. In southern hemisphere, it's just the opposite and looks like it's bending to the left. All right, so the Coriolis effect and wind. Remember, winds blow from areas of high pressure towards low pressure. So the Coriolis effect is going to make things bend to the right in the northern hemisphere and bend to the left in the southern hemisphere. This is the same for wind. So if we're watching the wind and this balloon, if we're in the northern hemisphere, it's going to turn to the right. This goes into our global wind patterns. Our atmosphere is very thick at the equator and pretty thin at our poles, okay? This is because colder air is more contracted, or it's more shrunken down, and our warm air is more expanded. This is what gives us our thicker atmosphere at the equator. So our global wind patterns. Our wind belts occur due to different latitudes having certain air pressures from differing insulation. In other words, we have either low pressure or high pressure at different areas because the amount of sun coming in is different. So at 0 degrees or at our equator, we have our intertropical convergence zone, which we also call the ITCZ, or our doldrums. This is a low pressure. 30 degrees north and 30 degrees south, we have what's called our horse latitudes. These are high pressure. 60 degrees north and 60 degrees south, we have our subpolar lows, which is a low pressure. And finally, right at our poles at 90 degrees north and 90 degrees south, we have our polar highs, or high pressures. Remembering, winds always blow from high pressure to low pressure. It's going to create our wind belts between these different pressure areas. They shift north during out of summer and south during our winter. All right, so when we look at these different areas of high pressure and low pressure, okay, and the Coriolis effect bending our winds, remember, to the right in the northern hemisphere and to the left in the southern hemisphere, okay? I have high air pressure at the poles, low pressure right here. So my wind is going to turn to the right because it's going from high to low and it's going to bend to the right. These are called our polar easterlies. At our horse latitudes, we have our high pressure. Again, our subpolar lows are right here. So our wind is going to blow from our high pressure to our low pressure, but it's going to turn to the right. We always name our wind from the main direction it's coming from. So this is mostly coming from the west. So we call it a westerly. Our next one, our high pressure is at our horse latitudes. Our low pressure is at our doldrums, or our ITCZ. Okay? So it's going to bend to the right. These are our trade winds. The same pattern is repeated in the southern hemisphere. We also have circulation cells. Since I have low pressure here at the equator, these are our doldrums, or our ITCZ, I have air rising. Air sinks at our at our horse latitudes at 30 degrees. That's why I have high pressure there. This circulation cell, or convection cell, of hot air going up, cold air going down, this is our Hadley cell. We find another area, goes up and comes down. Remember, convection cell, hot air goes up, cold air comes down. This is our Ferrel cell. And then our last one, our warmer air goes up here and sinks at the poles. This is our polar cell. So our weather versus our climate. Weather is the daily changes in the atmosphere. So this is very short term. And then our climate is our average temperature and precipitation for an area over a very long period of time. To help you remember this, you pick your vacation destination based on the climate, but pack your suitcase based on the weather. 4 factors that are going to influence climate. We have latitude, elevation, mountains, and proximity to water, or how close the area is to water. So when we look at latitude, this is how far north or how far south you are from the equator. Okay, the farther from the equator, the colder the climate becomes. So our climate zones that we have, 0 to 23.5 north and south, these are considered our tropics. Remember, this is our Tropic of Cancer, this is our Tropic of Capricorn. 23.5 to 66.5, these are temperate. This is where Virginia is. It's in a temperate zone. Okay, it's 66.5 to 90 degrees north and south. These are our polar climates. Elevation. As elevation increases, the pressure decreases, allowing air to expand and cool. This is called adiabatic cooling. This explains why there is snow on top of mountains, because it's colder on top of mountains. And then as elevation decreases, the pressure increases, causing the air to compress and heat. No condensation can occur if air is heating. Okay, so you can see once you go up higher and higher, as the elevation gets bigger, okay, it gets colder. So when we look at our mountains even closer, moist air goes up a mountain, it's going to cool. It's going to condense into a cloud and rain out all of that precipitation. Or if it's up high enough, it will be snow. Okay? When that same air starts to go down the other side of the mountain, it heats up and no condensation occurs, and we have a dry climate. Okay? So sinking clouds evaporate. This is going to create what we call a rain shadow. So usually one side of the mountain range will get all of the precipitation, all the rain and snow, and the opposite side will be considered a rain shower. So in other words, it will be considered a dry area. Okay, so here we see again, this side is going to get all the rain, this side could be a desert. The last climate factor, proximity to water. As a general rule of thumb, places near the water tend to experience smaller changes in temperature because the water takes a long time to heat and a long time to lose its heat. Close to the oceans, the air is more humid. You're going to have cooler summers and warmer winters. You're also going to have cooler days and warmer nights. And then if you're far from the oceans, the air is more dry, and you're going to have warmer summers and cooler winters and warmer days and cooler nights. This sounds confusing, but not so much. Our blue line, this is Dakar. Okay? You can see how it's pretty flat. There's not a lot of temperature change throughout the year. These are our months down here: January, February, March, April, May, June, July, August, September, October, November, December. So it goes from about 21 degrees Celsius, max probably about 28 degrees Celsius, and then it's going to restart for the next year. This other area, Timbuktu, which is very far inland, you can see it goes from about 22 degrees Celsius, going all the way up past 35 degrees Celsius, and then it's coming back down. So Timbuktu, this is what it looks like when it's inland. Dakar is what it looks like when it is next to the ocean. This shows a map of the United States, and you can see everywhere near the ocean we have lower temperatures. These are our surface temperature maps. Okay? Even cooler inside, and even cooler all the way to the furthest you can get from the oceans is the coolest temperatures that are seen. That's because, remember, our oceans take a long time to cool off, so it's holding some of the heat. So the areas next to it are going to stay more temperate throughout the year.